related rates is an application of implicit differentiation. So if you think back to last unit, implicit differentiation was when you had something like this, like x squared plus y squared equals 4. So that's the equation of a circle, and we wanted to find the derivative, but we didn't have y by itself, so this was 2x plus 2y, and then you had to follow it up with dy dx, because we are always deriving things with regards to x. And whenever you had the y variable, you had to follow up because it was the chain rule, because y was a function of x. So we had to take into account that y really was its own function and then follow up with the derivative of that function. The same thing is going to happen today in all of these related rates problems because, oopsies, we're going to be taking the derivative with respect to time. So we're going to have y's, x's, r's, h's. We're going to have a whole bunch of different variables in here. But we are always going to be talking about the rate at which something is changing at a certain moment in time. And that's why implicit differentiation is going to be important here, because we're going to be deriving with respect to time. All right, I think that's all I want to say there. So let's go on to the first example. Air is pumped into a spherical balloon at a rate of 5 cubic centimeters per second. Determine the rate at which the radius is increasing. All right, so let's picture this. When the diameter of the sphere is 20 centimeters. So it's a balloon, a spherical balloon. And as air goes in, the radius keeps getting larger and larger, 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 larger. So we want to, and at what rate is the radius getting larger? Well, it depends upon that exact moment in time. What's the volume at that time? What's the, well, we have the diameter. All these different things, and that's going to determine the rate at which the radius is increasing at that exact moment. So since volume and the radius vary with time, how much time have you been filling this balloon for? They are both functions of time. So that's why when we differentiate, we're going to follow up with the chain rule of, well, you'll see in a second. All right, so what do we know here? I always like, for these problems, I always like to make a list of what I know. So air is pumped into a spherical balloon at a rate. So I do know that the volume of a sphere is 4/3 pi r cubed. And if you don't know that, you will have that committed to memory very soon. And the problem tells me the rate at which the volume is changing with respect to time is 5 cubic centimeters per second. Okay, so I have that. And I think that's really all it tells me. So this is kind of an easy one to start. So if I want to know the rate at which the radius is increasing, I need to take the derivative of this because I want the rate at which the radius is changing. So it's okay that we're in two variables here. I know back when we did optimization last week, I always tried to get us down to one variable. This is okay to be in two variables because we're deriving with respect to time anyway. So we're having another variable come into play anyway. And these are all functions of time themselves. So the rate at which the volume of changing is equal to, now I'm going to derive this as it would be 4 pi r squared times the rate at which the radius is changing with respect to time. And now I should know, I should be able to plug everything in. So you guys are totally allowed to use a calculator today, although we're not going to use a calculator on this first one. We also know that the radius is 10, am I correct? Because it says the diameter is 20. So at this exact moment in time, the radius is equal to 10, and the rate at which the volume of changing is 5 cubic centimeters per second. So I'm not plugging in units until the very end. So this would be 100 dr dt. And now we're actually pretty much just able to solve for what we're looking for. We are looking for dr dt. So I just kind of put this in my list too. Like, what am I looking for? I want to find the rate at which the radius is changing. So let's say this is 5 equals 400 pi dr dt. And you can divide, I'm going to keep it as a fraction. So I end up getting 1/80 pi centimeters per second. So units are important here. So let's talk about that. were in seconds and were measured in centimeters. So the rate at which the radius is increasing is 1 over 80 pi centimeters per second. These take a little while to get used to, but let's go back and talk about what we did. Everything was based off of this, the volume of the sphere formula. So that's an awesome formula back in geometry. It was a lot of fun, blah, blah, blah. You could find the volume of something. Now we can find the rate at which the volume is changing, or the rate at which the radius is changing. So guys, I mean, you'll see in the next problem. We can talk about water, filling things up, all different things. I'm telling you, like, I can't fill a pot of water in my kitchen. So let's say I'm going to make some pasta without looking at the water going into this pot and saying like, oh, I can see the height is changing at a certain rate. And like, it's just insane what goes through my mind, how much related rates is a part of our lives. And that it's just something simple like this, like taking the derivative and finding a rate of change. And we can kind of figure these things out. So the next one's about a puddle of water, if I'm correct. Okay, yeah. So think about this. The next time it's raining outside and there's like a puddle forming like in your driveway, now your mind is going to go to something like this. I'm going to make sure I have a lot written down for this problem. Let me just make sure I said everything I want to say. Please realize that our answer is only, this is important. Please realize that our answer is only the rate at the single moment in time. So when the radius is equal to 10. This dr dt would be something else for when the radius was smaller or larger, depending upon how much air was in the balloon at that time. So this is like for an exact moment in time, our answer, which is really cool. And I think that's all I wanted to say for that one. All right, and guys, my answers are up on Canvas if you ever want to look at them. All right. Now we have our pool of water. A circular pool of water is expanding at a rate of 16 pi inches squared per second. At what rate is the radius changing when the radius is 4 inches? So this is another super easy one. So I'm glad we're kind of starting off easy here. So let's see what we're given. So it's a circular pool of water. So we know that the area of a circle is pi r squared. So I'm going to put that on the side because that's probably going to be our formula that we're going to go off of. We know that the rate at which the area is changing is 16 pi square inches per second. We know the radius at this given moment is 4. We want to know what is the rate. So find dr dt. What is the rate at which the radius is changing at this exact moment in time? So this is another super easy one. I can just tell by looking at the formula. So the rate at which the area is changing with respect to time is equal to 2 pi r dr dt. I don't know if you noticed anything fun about this last one. When you take the derivative of volume, you get surface area. When you take the derivative of the area of a circle, you get circumference. Pretty cool. All right, so now we just need to plug in because we're just looking for dr dt. We have the rate at which the area is changing and we have the radius. So we know for the exact moment in time that we are looking for, what is the rate at which the radius of this pool of water is changing. All right, so let's plug in. So this is 16 pi is equal to 8 pi. I'm just multiplying in my head here, dr dt. So this one's super easy. So 2, and let's get some units in there. So let's see, we're in inches per second. So 2 inches. Wow. So this is filling up pretty quickly. So the rate at which the radius is changing for this pool of water is 2 inches per second. So it's filling up pretty quickly, but that one's super easy. All right. Oh, I love ladder problems. Okay. A 25-foot ladder leans against a wall. The bottom of the ladder is being pushed towards the wall at a rate of 15 feet per second. How fast is the top of the ladder moving up the wall when the top is 7 feet from the ground? Oh my gosh, let's draw a picture. Okay, so we know the ladder is 25 feet. Okay, and that actually is something that can't change. That's going to be a constant throughout the problem. It's not like the ladder's length can all of a sudden just change. So that's going to be a constant. The bottom of the ladder, so this is our wall, is being pushed towards the wall at a rate of 15 feet per second. And I'm actually going to label that as negative 15. And if we were in class, I would ask you why. Why am I labeling that as a negative rate? And the reason is, if this is our x value, we'll say it's a horizontal, it's being pushed towards the wall, meaning the x is getting smaller. Okay, so it's a negative rate. I'll call this y, why not? And we want to know how fast is the top of the ladder moving up the wall when the top is 7 feet from the ground. So the 25 can't change. I know that this is going to be equal to 7 for this exact moment in time that we're talking about. And hopefully you guys recognize this is a right triangle. So I'm going to be using the Pythagorean theorem here. So x squared plus y squared. You could say, I'm going to say z, just because I used x and y. You could use a, b, and c if you really wanted to. So I'm going to take the derivative here. And yeah, I will. And then we'll simplify it. We won't have to do this every single time. So this will be 2x, and then the rate at which x is changing with respect to time, which we already knew, that was given to us, plus 2y dy dt, which I think is what we're looking for, right? How fast is the top of the ladder moving up the wall when the top is 7 feet from the ground, is equal to 2z dz dt. Okay, so notice, guys, in all of these problems, I'm not plugging in what I know until I take the derivative. It's not helpful to plug into this formula because that has nothing to do with the rates. So I'm not plugging in until I take the derivative. And I'm going to simplify this. I'm going to divide everything by 2, which is what I was going to do at first, but I didn't want you guys to think I was cheating steps or anything. Okay, and in the future, you can always just jump to this when you have a right triangle problem. Okay. So we're talking about the triangle being at a certain moment in time, and the moment in time is when the height here, the y, is 7. So let's fill in what we know. We know dx dt is equal to negative 15. I know that z is equal to 25. What would dz dt be? We do know it. So the rate at which z is changing with respect to time is 0. Because this length is not changing. The 25 stays, which is beautiful because it's going to turn the right side of our equation into 0. So now I know y is equal to 7. I know I'm looking for dy dt, so I still have an unknown in there, right? I know dx dt, but I don't know x. So I just need to use some common sense. This is a right triangle at this exact moment in time. If this is 25 and this is 7, this is equal to 24. I would just use the Pythagorean theorem there. So I have so much to fill in here, but there's only one unknown. This is going to be 24 times negative 15 plus 7 times dy dt. That's what we're looking for. The rate at which y is changing with respect to time is equal to 0. Because dz dt is 0, so I could have written 25 times 0. I don't feel like writing it. Okay, so I'm just going to go ahead and solve here. So what do I get? I get 7 dy dt is equal to, now you guys have access to a calculator for these, so I have my answer key in front of me, so I'm just using it. 360 dy dt is equal to 360 over 7, and we'll turn that to a decimal, why not? So that would be 51.429. What are our units here? Feet per second? Yes, feet per second. And that's the rate at which this segment is changing at that exact moment in time. If we were talking about a different moment in time, the rate would be different. So let's talk about important things here. dz dt is 0. The length of the ladder does not change, so the rate at which it's changing is 0. If a segment is getting smaller, its rate is negative. I think that's all I wanted to point out on that one. Ooh, number 4. All right. A tank is in the shape of an inverted cone. A tank in the shape of an inverted cone is leaking water at a rate of 2 cubic feet per hour. The base radius of the tank is 5 feet and the height of the tank is 15 feet. Oh my goodness. I hope I have enough space here, considering I gave you guys a whole page. All right, let's do it. So I'm going to draw myself a little picture here, and I'm really just going to look at a cross section of this cone. What I do know is that the volume of a cone is equal to 1/3 pi r squared times h. And now I have an issue. I'm in 3 variables, and that's where things can get really ugly. If I try to take the derivative right now, I'm going to have the product rule, and that's okay, The problem is that we'd have dr dt and dh dt. And we don't know dr dt. If I'm looking at the problem, it was not given to me. And if you look at part A, it's only asking me to find dH dt, the rate. I'm not looking at B yet. The rate at which the water in the tank is changed, the depth of the water. All right. So if dr dt doesn't matter, I'm going to try to get rid of R from my formula before I take the derivative, because I don't know dr dt. And if I did product rule there, I would have to figure out dr dt, and I don't have enough information to do that. So the secret is to eliminate R or H before taking the derivative. And in this case, we want to eliminate R. If you're looking at part B, if you're sort of looking ahead, you kind of have to go back and eliminate H. So let's figure out how the heck we can do that. So I'm going to go back and take a look at the information that was given to me. So the radius of the tank is 5 feet and the height of the tank is 15 feet. Okay. At any given moment in time, I'm going to change my color here. I could draw in a different height for how full the tank is and a different radius. But hopefully you're recognizing something here. Is this is a right triangle, this is a right triangle. We have similar triangles. Okay, so this is the height and this is the radius. Well, I don't care what the height and the radius is at a given time. It's going to be proportional to the height and the radius of the overall cone. So this is awesome. This is such an easy proportion to set up, and we're going to be able to eliminate R or H pretty quickly. So I know that 5 over 15 is going to equal R over H. Because I have similar triangles here, I'm allowed to set up a proportion. So what do I have here? 15R is equal to 5H. And what am I trying to, I'm trying to get rid of R here, right? So let's say let's say R is equal to 1/3 H. And I am going to kind of go ahead and do it the other way around and say H is equal to 3R, depending upon what we need. I'll put that over here because now I'll be able to plug in for parts A and B. So I'm going to do part A over here. So guys, I've been talking a lot through this problem, and I've kind of been explaining what I had written down on my answer key. And I didn't write all that out here. So if you need to look at my answer key to read some of those explanations again, feel free. So I know the volume is equal to 1/3 pi r squared times the height, but I want to know what is the rate that the depth of the water is changing. So I want to keep H and get rid of R. So R is equal to 1/3 H. So I'm going to plug that in. So pi 1/3 H squared times H. So let's simplify this. So the volume is equal to, what's that, 1/27th, right? Because the 3 gets squared. So 1/27th pi H cubed. And now I'm ready to differentiate. I'm going to be able to find dH dt because I know, what do I know? I know the rate at which the volume is changing with respect to time, right? The tank, it's leaking water. So right away, that tells me it's a negative rate. So dV dt is -2. And when the depth of the water, so I know that H at this exact moment is equal to 6. So once I differentiate here, I'm going to be able, so the rate at which the volume is changing is equal to 1/9 pi H squared dH dt, the rate at which the height is changing with respect to time. So I'm going to fill in, I know this is -2 is equal to, I'll write it out, 1/9 pi times 36, because it's 6 squared, dH dt. So that's -2 over 4 pi. Hopefully you guys are following my algebra there. 36 divided by 9 is 4, is equal to dH dt. And I did keep it in this. You could change it to a decimal if you wanted to. So I said this was -1 over 2 pi. And what are my units? Feet per hour. Equals the rate at which the height or the depth of the water is changing. Easy peasy. And part B is pretty much asking us the same thing, except it's saying at what rate is the radius of the water level changing when the depth of the water is 6 feet. So we have a little bit more work to do here. I need to use my proportion. So I know that 5 over 15 is equal to R over H. So if we're talking about the moment when the depth is 6 feet, so that's 5 over 15 equals r over 6. 30 equals 15r. So we're talking about the moment when the radius is equal to 2. Because remember, if I want to know the rate at which the radius is changing, I don't care what the depth is at that moment. I'm going to get everything in this formula in terms of r. So I'm going to say volume is equal to 1/3 pi r squared times what? We know that h is equal to 3r. So this actually cancels out really nicely. So the volume here is equal to what? Pi r cubed? Yeah, cubed, not squared. So the rate at which the volume is changing at this exact moment, so it's still when the depth of the water is 6, so dv dt doesn't change because we knew the rate at that moment. Oh, actually, yeah, and it's just leaking it at a constant rate, it looks like, is equal to pi, let's say 3 pi r squared dr dt. Sorry, I'm trying to fit everything in. I'm going to come up here. So now we can fill in. -2 is equal to, now we know the radius is equal to 2 at this point, so that's going to be 12 pi dr dt. So the rate at which the radius is changing at this exact moment in time is -1 over 6 pi. And that, again, is feet per hour. And again, I would let you give it to me in decimals. Even though calculator isn't completely necessary here, I would let you be using one. And your decimals just need to be rounded out appropriately to 3 decimal places, appropriately and accurately. All right, so that was a lot. But guys, look, there's a lot written on my answer key there. I was speaking a lot of that and not writing it. All right, we have 3 left. I wonder how long this is. I really need to pay attention to what time I start the videos. All right, this one looks pretty quick. Yeah, all right. A spherical balloon is expanding at a rate of 60 pi cubic inches per second. So that's talking about volume. Uh-oh, how fast is the surface area of the balloon expanding when the radius is equal to 4 inches? All right, so they tell us something about the volume, and then they want to know how fast is the surface area changing. So we know the surface area of a sphere is equal to 4 pi r squared. I know the volume of a sphere is equal to 4/3 pi r cubed. And we want to know, all right, so we want to know dSA dt. We want to know the rate at which we want to find that. The rate at which the surface area is changing. So the problem is that I don't know dr dt. So if I was going to take the derivative of this right now, it's going to be equal to 8 pi r dr dt. And I have 2 unknowns. I want to find the surface area, the rate at which the surface area is changing. They told me the radius is 4 at this moment, but I don't know for the exact moment in time what the rate is that the rate at which the radius is changing with respect to time. So I need to use this formula as a hint, right? I know dv dt, the rate at which the volume is changing, is equal to 4 pi r squared dr dt. And what's nice is that I can plug in for the moment in time when the radius is 4 inches and find out what the rate is that the radius is changing at that given moment based upon the given information. So I can plug in the 60 pi here. 4 pi times 16 is equal to dr dt. I'm sorry, times dr dt. And what do I get here? Dr dt, what's that going to be, 60 over 64? The pi's are going to cancel. So dr dt, I'm going to simplify that, is equal to 15 over 16 inches per second. You guys can check my algebra on that, but it looks pretty good on my paper. All right, so now I can plug in. I know the radius and I know the rate at which the radius is changing at that given moment in time. So I'm going to be able to solve for the rate at which the surface area is changing with respect to time. So I had to use this other formula to find a piece that I needed over here, but it really wasn't that bad. So the radius is 4, and this is times 15 over 16, because we just found dr dt. So I plug it all in, multiply. You can do it on your calculator. I am getting that the rate at which the surface area is changing with respect to time is equal to 30 pi. Now let's think about units here. Surface area, square inches per second. Okay, 2 more. Oh, the shadow problem. Okay, so a 6-foot tall man is walking towards a street light at a rate of 2 feet per second. If the light is 24 feet tall, at what rate does the length of the man's shadow change at the point when he is 6 feet from the light? Okay, so I have a little bit of a video to show you here. Let's see if I can bring this up. Walking toward the light. I can show you the walking away from the light video too. So I just want to show you right here. When you're walking toward the light, this is, I'm like pointing to the screen like you can see it. Your shadow is behind you, and you can see that the shadow, the closer you get to the light, is getting smaller and smaller and smaller. But if you look here, it almost looks like we have similar triangles again. So let's kind of draw this out. We can even watch that one more time. So the shadow's behind me as I'm walking towards the light, and my shadow is slowly getting smaller. But we definitely do have another similar triangle situation. And if this ever comes up, I'll show you this video too. This is if you're walking away from the light. So you're going to see your shadow is now in front of you and getting larger. But once again, you still have your similar triangles. But this is not what's happening in the problem that we're talking about, but I just did want to show it to you. Okay, dude. Oh no, cancel. Okay, so let's draw a picture. All right, so this light is 24 feet tall. He's a 6-foot tall man. So this is his shadow, and I'll just call this X. So his shadow is Y, but as he gets closer to the light, his shadow becomes these two together. But I have my similar triangles very clearly here. So 24 over X plus Y is equal to 6 over Y. So let's just cross multiply. 6X plus 6Y is equal to 24Y. 6X is equal to 18Y. And this is super easy. So I just have to differentiate right now. And I know the rate at which he's walking towards the light. And I'm almost done, right? So the fact that he was 6 feet from the light doesn't matter. So it must be a constant. Doesn't matter how far you are from the light, the rate it's changing must be constant. So this is 6 times dx dt. Oh, that's why it doesn't matter. So there you go. Dx dt is equal to 18 times dy dt. So let's see, what do we know and what was given to us? Perfect. Okay, so he is walking towards the light, so x is getting smaller. So we know that dx dt is equal to -2 because x is getting smaller as we walk towards the light. And then we're looking for the rate at which his shadow, so this is his shadow, the rate at which his shadow is changing. So let's see. And the shadow should be getting smaller, right? We said the closer you get to the light, the smaller. So the rate, the dy dt, should be negative. Let's see, 6 times -2 is equal to 18 times the rate at which the shadow is changing with respect to time. So that's -2/3 is equal to dy dt. And let's see, that's feet per second, right? -2/3 feet per second. So the distance from the light was meaningless because we only needed to know dx dt when we did the derivative anyway, because the derivative it was just 6. So it didn't matter that he was 6 feet from the light. There was no x to actually plug in. All right. Awesome. One more. Ooh, I love this last one. All right, the rocket is rising vertically at a rate of 50. Oh, okay, so this one's going to involve some conversions, if I remember correctly. A rocket is rising vertically at a rate of 5,400 miles per hour. An observer, yeah, because see how it's in seconds here? I can tell already we're going to have to convert. So that's something you just want to be on the lookout for, is just like make sure your units are staying consistent within the problem. An observer is on the ground 20 miles from the launch point. How fast in radians per second? So we want to make sure our calculators are in radians. There is never going to be a problem where you ever have to be in degrees. Your calculator should always be in radians. How fast is the angle of elevations between the ground and the observer's line of sight changing when the rocket is 40 miles high? Okay. So we know that he's 20 miles from, and that's the angle of elevation. Okay, so at this exact moment in time, so this to me looks like it's going to be, so this is the height is y, but at the exact moment in time we're talking about y is going to be equal to 40. So this to me looks like a SOHCAHTOA problem actually. So I know the tangent of theta is equal to y over 20. So I'm not plugging in the numbers I know yet until I take the derivative, because that's when it matters. And we're going to have to find some things in here. We're going to use our calculator. That's okay. So I know this would be secant squared theta d theta dt, the rate at which the angle is changing. That's what we're looking for, right? Is equal to 1 over 20 times dy dt. So I just took the derivative there. And I should be able to, I need to use this 40. I'm not plugging it in. Oh, I know what I can do. But what I can do is find the value of theta at that exact moment in time, because that's what I need. So let's do this. Oh yeah, we need dh dt too. All right, we're going to do both of them. That's fine. So let's do this. I have a right triangle. Does not look accurate at all. This is 20, this is 40 at this exact moment in time. I know the tangent of theta is equal to 40 over 20. So I'm going to go into my calculator. I'm going to make sure I'm in radians. And I'm in degrees, so there you go. I was just doing navigation problems with pre-calc. You guys remember those? Got to be in degrees for that. 40 over 20, is that what we said? So I'm getting that my theta is 1, and we're going to round accurately, 1.107 radians. Okay, so that's theta. I have that there. The other issue is that dy dt, well, we know what it is in miles per hour, but we need to be careful because we want to know what it is in miles per second, because we're looking for d theta dt in terms of seconds. So I'm going to do a quick conversion down here. I know that it's going 5,400 miles per hour. So I'm just going to convert real quick. 1 hour is 60 minutes. 1 minute is 60 seconds. And I'm going to get that this is 1.5 miles. So I did that in my calculator. I'm just taking it from my answer key right now. 1.5 miles per second. So that's what my dy dt is in the correct units. So just be careful there when you're plugging in. So now I think I have everything I need to plug in to find d theta dt. So secant squared of 1.107 d theta dt is what I'm looking for, is equal to 1 over 20 times 1.5. Okay, and then I'm going to go ahead and solve, and you're going to get a decimal. Go ahead and do it in your calculators. D theta dt. I'm going to put this to the side here so that we can see our answer. I'm getting 0.015 radians per second, and you guys can check that on your calculators. All right. What a fun group of problems. I hope I didn't do them too quickly. I hope my explanations were clear. Obviously, this is something we need to practice a bunch, but I hope you enjoyed it. So those of you in school tomorrow, we're actually not going to be doing related rate stuff. We're going to do a different activity that kind of has to go back to curve sketching that I always do, and we just haven't been in school to do it. Those of you that are at home tomorrow are going to practice relating rates, and then we're going to flip-flop. All right, guys, I will see some of you tomorrow. Bye-bye.